Now we will practice developing the initialization of a loop in a way that answers only the first loopy question. The goal is to find an initialization that truthifies the following statement. The execution of the initialization given Q is guaranteed to terminate with P true. Let's look at our first example of precondition Q and invariant P. Q is M is no greater than N. P is S is the sum of M dot dot K minus 1 and M is at most K and K is at most N. The initialization step requires us to use only simple variable assignment statements. We can calculate the sum of a range of values, as the invariant requires us to, using simple assignment statements, but only if that range is either empty or contains only one value. In this case, the range M dot dot K minus 1 is empty if K is equal to M. That is, the range equals M dot dot M minus 1. The initialization is therefore K becomes M, S becomes 0. Note that the range M dot dot K minus 1 could be empty in this case, so we have to start off with K is equal to M. Now we will look at another case, one where the range cannot be empty. Here are the precondition and invariant for a loop to calculate the minimum value in an array segment b sub 0 dot dot n minus 1. The precondition Q is n is greater than 0. The invariant P is v is equal to the minimum of b sub 0 dot dot k minus 1 combined with k is no less than 0 and no greater than n. Because the minimum of an empty set is not defined, the initialization cannot make range 0 dot dot k minus 1 empty. Instead, the initialization must make the range contain a single value, b sub 0. The initialization we will use is therefore k becomes 1, v becomes b sub 0. This satisfies the invariant because the range 0 dot dot k minus 1 only contains one element, b sub 0. That element is therefore the minimum of the elements in that range. The general rule is, in any situation where invariant P contains a range, the initialization usually makes the range contain either 0 or 1 values. Be aware of this situation. You will see it over and over again. Initializing to an empty range, like in the first example, is quick and easy. The second example reminds you that you have to think. You can't just blindly apply what we did in the first example to every problem. A lot of problem solving in computer science and math deals with recognizing patterns and learning from them. This example illustrates this idea of pattern matching. Consider calculating b to the power of c for c greater than or equal to 0. Here are the precondition Q and invariant P. Q is c is no less than 0. P is b to the power of c is equal to z times x to the power of y, and y is greater than or equal to 0. The initialization must store values in z, x, and y that make invariant P true. Note that we don't set initial values for b and c because these values are given to the algorithm. They do not change. Since we see that in the invariant, both sides of the equality contain exponentiation, we are encouraged to follow this pattern, assigning b to x and c to y. Because Q says that c is no less than 0, we can say the same of y. This satisfies the second half of the invariant, that y must be no less than 0. To make the first half of P true, z must now be equal to 1. This yields the following initialization. Z becomes 1, x becomes b, y becomes c. This satisfies the following statement. The execution of the initialization given Q is guaranteed to terminate with P true. Now please complete the following exercises, which require you to find the initialization for the given precondition and invariant. The answers can be found at the end of the document accompanying this video.